Hello everyone, I'm Adam. In this problem, for our given sum, we have here sum from I equal 1 to n of 3 over n cubed times the quantity 1 plus I squared. What we want to do is first try and take this sum and rewrite it as some rational expression, which we'll call s of n. And then, with that s of n expression, we're going to try to complete our table over here. And then finally, we're going to take the limit of our sum by taking the limit as n goes to infinity of our sum s of n. So let's start with part A here. So I want to try to rewrite the sum as some rational expression. So some s of n is going to be equal to, starting out, our sum from I equal 1 to n of 3 over n cubed times 1 plus I squared. Right. Now, taking a look at this, so n sitting up top as far as the sum is concerned, as well as our 3 right here, they're just going to be considered constants, right? So what does the sum mean? We would take I equal to 1, plug it in for I equal to 2, plug it in for I, and then successively add all these pieces up until we get up to whatever number n is. But within the sum, we can just factor out anything that's considered a constant, right, or it isn't involving the term I. So that's what we can start to do by bringing this outside and making our work just a little bit simpler. So we can write this as 3 over n cubed, and then times, now when we have a sum or difference of things, we can move in and take the sum of each. So this will be 3 over n cubed times the sum from I equal 1 to n of just 1, and then plus the sum I equal 1 to n of I squared. Okay? And so this is going to be 3 over n cubed. All right, and we'll simplify the inside. So the sum of just the constant 1 from I equal 1 to n, so essentially we're just taking the number 1 and adding it together n times. So if n was equal to 5, you add the number 1 with itself 5 times. What's the overall sum equal to? Well, 5. So with here just our general constant n up top, so summing that, I equal 1 to n, we'll just have n. And that's going to be plus. Now the sum from I equal 1 to n of I squared, right, we have a formula for this as far as what this sums out to. So adding this is going to be equal to n times n plus 1 times 2n plus 1 all over 6. Okay, so essentially we have we're on our way towards getting a rational expression, but we're just going to simplify the inside here. So we'll have 3 over n cubed. All right, so we want to add n with our part over here. We'll get a common denominator, so we can take top and bottom times 6, or 6n over 6. And we're going to add it with this expression here. And we'll simplify that by kind of multiplying out the top. So first, we'll take n times n plus 1 would give us n squared plus n. So now we can FOIL out our n squared plus n, say with our 2n plus 1. And so n squared times 2n, we get 2n cubed, n squared times 1, so plus n squared, n times 2n, plus 2n squared, and n times 1. We have plus n. Okay, now over a common denominator, we can add the inside. This will be 3 over, say, n cubed, all over a common denominator 6. So combining like terms, we have 2n cubed, n squared plus 2n squared, it was plus 3n squared, and 6n plus n, so it would give us 7n. Okay? Now, a couple last things we can do. We see multiplying this entire expression by 3 over n cubed, the 3 will cancel with our 6, and we'll have a 2. And we see we have a common factor of n that can be brought out in the numerator, so which will cancel with one of the n's on the bottom, leaving us with an n squared. So we'll cancel with that n. One of the n's here, leaving us n to the first, and one of the n's here, leaving us with n squared. So let's clean this up. Put it here. So our rational expression, we're going to have our numerator, say 2n squared plus 3 times n plus 7, and the denominator, right, n squared times 2, so 2n squared. Okay, so what we've done is we've written our sum as a rational expression. So that completes part A. So now for part B, what we want to do is use this rational expression, right, to fill out our table here. Now, before we go on and do that, again, what we have is this rational expression written for our sum is essentially a formula, a user-friendly formula if you want to call it that. So looking at the sum, right, if we change the value of n, so if we wanted to find the sum from I equal 1 to say 5, we would have to go through and add 5 separate terms to get what the sum would be. When n is 6, you'd have to add all 6 terms. Being that this sum is essentially equal to this rational expression, now for whatever value n we're going to sum to, we can just plug that value n in and get what the sum would be. So it saves us a lot of work. So onto our table. We're going to use our calculator to help us. Okay. And first, okay, so for the values of n that we have here, we have 10 to the 0 power. We'll just write these a little more user-friendly. So 10 to the 0 is just 1. 10 to the first is 10. 10 squared, 100. 10 cubed would be 1,000. And 10 to the fourth, we get 10,000. So for each value of n, we're going to plug that in. Okay, looking at our rational expression, so for 10 to the 0, or 1, we'll have 2 times 1 squared plus 3 times 1 plus 7, and all divided by 2 times 1 squared. So that gives us a value of 6. And next, so plugging in 10 to the first, or just 10, so 2 times 10 squared plus 3 times 10 plus 7, all divided by 2 times 10 squared. So it gives us something like, say, 1.185. And for 10 squared, or 100, same thing, 2 times now 100 squared plus 3 times 100 plus 7, all divided by 2 times 100 squared. And that's going to give us something like 1.0153. And next for 10 cubed, or 1,000, so 2 times 1,000 squared plus 3 times 1,000 plus 7, and all divided by 2 times 1,000 squared, which gives us something approximately equal to 1.0015. And lastly, for 10 to the fourth, or 10,000, so we'll have 2 times 10,000 squared plus 3 times 10,000 plus 7, all divided by 2 times 10,000 squared. And that'll give us something approximately equal to, say, 1.0002. Okay, so that completes part B. And there's actually kind of a segue here. All right, so what we were really doing is, with our summation, if we take progressively larger and larger and larger and larger and really large values of n, like when n is 10,000, what is the sum getting close to? It's kind of a question we might ask. So we can see as we start out, when n is really small, we get the value 6. And all the way down here, when n is getting bigger and bigger and bigger, it looks like it's getting closer and closer to the value 1. which essentially is what we're going to answer for part C. So when we take a look at C, we're looking at the limit, right, as n goes to infinity of our sum S of n. So essentially, if we were to sum this for larger and larger values of n, what would that approach is what we're asking here. And so that's equal to the limit as n approaches infinity. And we can use our expression. So taking the limit of 2n squared plus 3 times n plus 7 all over 2n squared. Okay? Now, if we take a look at this rational expression, we see that the highest powers on top and bottom are equal to each other. So as n approaches infinity, this limit is just going to be equal to the ratio of the two leading coefficients. So 2 over 2, which 2 divided by 2 gives us the number 1. So there we go. Thank you very much.